Hello students, so this is the second part of chemical properties of chemical trends in the periodic table of various elements, right? Under this, the second part, first one was valence or oxidation state, the second one is anomalous properties of second period elements. This is again very important property shown by the second period elements. All the second period elements, they show certain abnormal characteristics than the rest of their members. Okay, the first element of each group, that is lithium, as shown in the diagram. Lithium is there, then beryllium. These all they belong from the second period, right? Boron, then carbon, nitrogen, oxygen, fluorine, neon. So second period elements are given. And then along with that, third period elements are also shown. Okay. Now these second period elements, lithium, beryllium, then 13 to 17, that is boron to fluorine. We are excluding this neon, noble gas. Differ in many respects from the other members of their respective groups, right? So that's why we call them as anomalous, because they show variation or difference, right, than the rest members. For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals. So lithium and beryllium, right? Lithium belongs from group 1, beryllium from group 2. They both form compounds with pronounced covalent character. Although first and second group elements, they are generally ionic in nature, right? But they have these two elements, that is lithium from first group and beryllium from second group. It has a more covalent character, right? The other members of this group, right? Predominantly they form ionic compounds. In fact, the behavior of lithium and beryllium is more similar with the second element of the following group, right? That means, now this is an interesting factor, that is lithium has more similarity with magnesium, right, which is present diagonally. That's why it is called, that such a relationship is also called as diagonal relationship, whereas this beryllium, it has its relation or its properties similar to that of aluminium, right? These two, and lithium and magnesium, okay, respectively. This sort of similarity is commonly referred to as diagonal relationship in the periodic properties, okay. In the same manner, boron and silicon, they can also show diagonal relationship. So generally, we analyze the diagonal relationship on moving from left to right, from this direction, and between the elements of second and third period elements. Which elements? Second and third period elements only, right? Otherwise, diagonal relationship can be between any two, from left to right, right to left, right? But we just take into consideration these elements. Lithium and magnesium, they show diagonal relationship, beryllium and aluminium, and boron and silicon, right? So diagonal relationship is the similarity in the properties of the elements which are present diagonally in second and third period elements on moving from left to right, okay. Now, again, to the anomalous properties of second period elements. Anomalous behavior. Now, why they show different or variation in properties? It is attributed to their small size. So, first reason is their small size. This is very important. Number one, small size. That is large charge radius. Large, whenever cations are formed, so they will have very high charge. So, this one will be second property, second reason for showing abnormal properties. And then radius ratio in the same manner, and high electronegativity of the elements. So these are the two factors, and third one is high electronegativity. Electronegativity, we will just limit this to covalent compounds or non-metals, right? Whereas radius ratio comes out in ionic compounds, okay. In addition, again this is important, the first member of the group has only 4 valence orbitals. First member of the group. Now again, if we take example of let us say boron, right? Boron belongs from group 13. So its electronic configuration will be outermost shell. So 2s2 2p1, right? 5 electrons are there, out of which 2 are in 1s2. So this is inner shell and the outer shell is this. Now how many orbitals? So for S generally we represent 1 orbital, and for P we represent 3 orbitals. So in total there are 4 orbitals for bonding. 1, 2, 3, 4. So their covalence of maximum covalency of this second period elements, it will be 4, right? Covalency, okay, due to availability of these 4 orbitals, right? Now as a consequence of this, the maximum covalency of first member of each group is, for example, boron can only form. Now this is the compound of boron. This is tetrafluoroborate. Whereas other members of the group, that means third period onwards, right? For example, if we talk about nitrogen, it is below. It is in second group, and then nitrogen has 2s2 2p3 electronic configuration, right? Again 4 are there, 4 same orbitals will be there, 2s and 2p. Now nitrogen is second period. If we go downwards, so we will get phosphorus. Which species is there? Phosphorus is there. So phosphorus has atomic number 15. Its valence shell will contain neon is there, noble gas, then 3s2 3p3. But do remember that it has empty 3d orbitals, right? Empty 3d orbitals means now it will have 1 orbital of 3s, 3 orbitals of 3p, and 5 vacant orbitals of 3d, okay? 5, 3d, 3p, and it will be 3s. So how many orbitals are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 orbitals are there. Whereas in this case, in second period elements, there were only 4 orbitals. So that means the covalency can be extended now. Okay, that's why it's given here that boron can form only this, whereas the other members of the group can expand their covalence shell to accommodate more than 4 pairs of electrons, right? For example, aluminium forms AlF6 3 negative hexafluoridoaluminate. Okay, so this is due to availability of these 5 vacant d orbitals, right, which is missing in case of second period elements. So this is the 4th reason, right? So there are 4 reasons which on the basis of which we can explain the anomalous properties or anomalous behavior shown by the second period elements. Then the third one, okay? Now then the first members, due to their very small size of p block elements, particularly group 13 to group 18, have greater ability to form p pi multiple bond. Means they can form multiple bonds within themselves, right? For example, in carbon double bond, carbon triple bond. This is in case of alkynes, and this is found in case of alkenes. In the same manner, nitrogen can form a triple bond, or sometimes in azides double bond is also formed, right? To the other second period elements, or they can form among themselves also. For example, carbon and oxygen, carbon and nitrogen, right? These bonds may be there. So this double bond formation property is limited to small size and large charge. So that's why the orbitals, they can undergo overlapping to greater extent, and thereby resulting in pi bond formation. We will discuss about this pi bond later on in 4th chapter. Okay. So due to these 4 reasons, right, the second period elements, they show abnormal or anomalous properties. Now based on the same, there is a problem. Are the oxidation states and covalency of aluminium in aluminium Al, Cl, H2O 5 times, 2 positive, same? Dear students, such compounds are called as coordination compounds. What we call them? Coordination compounds. These are complex compounds. These are complex compounds. Okay, and it will be named as penta aqua chlorido aluminate aluminium 2, not aluminate, aluminium 2, right? So this is a complex. Now what's the question? That are the oxidation state. So first we have to calculate oxidation state of aluminium, and secondly we will find out its covalency, right? So first of all, aluminium belongs to which group? Group 13. Below boron it is present. Atomic number is 13 again, right? Electronic configuration will be neon, then 3s2 3p1, right? So this will be the electronic configuration for aluminium. Okay, or if I represent it like this, so 2 electrons will be in this 3s orbital, and then 3p contains 3, so it will have only 1 electron, and then vacant 3d orbitals are there, right? These are 3d orbitals, 3p. Clear? This is on the basis of electronic configuration. Little bit we have already discussed, right? Now this is the ground state representation for aluminium. Now aluminium, how many valence shell electrons are there? 3. So it can extend it up to here, right? And as a result, 3 electrons will be available for bonding. So what will be the oxidation state of aluminium? So it can release 3 electrons, so its oxidation state can be plus 3. It will not gain electron, rather it will release. Okay, if the compound is ionic, but oxidation state will be limited to plus 3. So first part is clear. Now we move to the covalency. Covalency means we have to analyze the structure of this. Actually this aluminium is the central atom and it has octahedral shape like this. These 4 will be in one plane, right? Something like this. Now that means aluminium has formed 6 bonds, or 6, it has attached with itself 6 species. 5 of them are water, H2O, 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 5, and 1 is Cl, and then charge is there 2 positive. Okay, this will be the structure. Now coordination number or covalency. Covalency is limited to coordination, that how much orbitals, how many orbitals have been involved for the formation of this bond. So as you can see that aluminium 1, 2, 3, 4, 5, 6. So its covalency, that is 6 orbitals are involved because it has resulted in 6 bond formation. So its covalency will be 6. So that is the second part. Okay, how many bonds it has formed, that will give you the covalency, or how many orbitals are involved in this bond formation. Okay, so s orbital will be involved, all the 3 and 2, 3 plus 1, 4 and 2 from this. These orbitals are involved for bond formation, whereas such properties are not available in second period. They don't show such property because of non-availability of D. So D orbitals, they are involved in bonding, hence as a result of that rest group members, due to availability of 3d or d orbitals, they can extend their covalency beyond 4. In this case its covalency is 6. Okay, now we will check this. So the answer is, are the oxidation states and covalency of the same? No, right? So covalency and oxidation states are different. Oxidation state of aluminium was 3 and covalency is 6. Okay, I hope this is clear to you. Then we move to the next part, that is trends in chemical reactivity, the next part, and this is the last one. General trends are given. All chemical and physical properties are manifestation of electronic configuration, right? So all the physical and chemical properties, they arises due to the electronic arrangement, as we have already discussed as per the modern periodic law, right? That the chemical and physical properties of elements are periodic functions of their atomic number, and atomic number is related with electronic configuration of the element. We shall now try to explore relationship between these useful fundamental properties of elements with their chemical reactivity. So whatever properties we have analyzed, we will try to correlate them. Okay. For example, atomic and ionic radii, right? Atomic and ionic. Just to recall, atomic and ionic radii, as we know, generally decreases in a period, right? Both atomic radii as well as ionic radii. That's why the size of fluorine is smallest, right? Because the size goes on decreasing, or radii goes on decreasing along the period, right? From left to right. As a consequence, the ionization. Now, can we relate size with ionization enthalpy? So, radii can be related that it will be inversely proportional to ionization enthalpy. Okay. Then, ionization enthalpy generally increases as we move along the period. That is, fluorine has maximum ionization enthalpy. And likewise, electron gain enthalpies become more and more negative across the period. So, I think it is clear, we have already discussed all these. In other words, the ionization enthalpy of extreme left means this one, alkali metals or alkaline earth metals, is the least because they have biggest size, and electron gain enthalpies of the elements on the extreme right are highest negative, that is fluorine, oxygen, this part. Okay. Noble gases, as you know, they have positive values due to fully filled electronic configuration, already discussed. So this results into high chemical reactivity at two extremes and the lowest in center. That means due to this tendency to release electron, these two alkali and alkaline earth metals, they have greater tendency to release electron. They will release electron. So they will become electropositive. That means we can relate it with their metallic character, and reactivity, they will be more reactive. Then the species which are present towards right side, because they have the greater tendency to gain electrons, so they will gain one electron and they will become negatively charged. So both the extremes of the periodic table, left side and right side, they are highly reactive. One being electropositive, we can relate, that is metallic, and another being non-metallic. Okay. The maximum chemical reactivity at the extreme left, right? Extreme left means towards alkali metals, is exhibited by the loss of an electron, leading to the formation of cation at the extreme right among halogens, shown by the electron gain, so forming an anion. So both these can be related. So if these species, they form M positive, the other species which are present on the extreme right, they will form X negative, and as a result, these are also reactive. These species both are reactive, and they try to form the compounds, and most of these compounds, they are ionic in nature, right? This property can be related with the reducing and oxidizing behavior of the elements. Dear students, reducing and oxidizing nature, that is related with tendency to release electron, and thereby itself it will get oxidized, right? And then other species which has gained electron, that get reduced. This property we will discuss, but right now we will relate it with metallic and non-metallic character. So these properties, they can be related to the metallic and non-metallic character of the elements. This is the metallic character of an element which is highest at the extreme left, right? These are highly metals, M. And non-metallic character increases on moving right to left. That is, on the extreme right side, it's non-metallic character that goes on increasing, whereas on the extreme left side, it will be metallic character. Now I think these all the properties are clear to you. Okay. And across the period, metallic character decreases, and downwards what happens? Downwards, non-metallic character goes on decreasing, or metallic character increases, right? The chemical reactivity of an element can be best shown by its reaction with oxygen and halogens, right? Now, oxygen belongs to group 16. Oxygen belongs to group 16. Oxygen 16 group contains oxygen, sulfur, selenium, tellurium, and polonium. This is group 16. And group 17 are fluorine, chlorine, bromine, iodine, and astatine. Right? So, most of the reactivity, most of the compounds which are formed by these, they will be, or properties can be related by the reaction of these species with the oxygen and halogen. Both are highly reactive species. Now we will take into consideration the reactions of some of the elements with oxygen, right? Likewise, they will combine with halogens also, but our focus will be on oxygen. Elements on two extremes of a period, right? Two extremes, again left and right side of the periodic table, easily combine with oxygen to form oxides, right? So oxides will be formed. Any binary compound of any element with oxygen is called oxide. Then that means metal can also form oxide, right? Depending on the valency, as well as non-metals can also form, right? That will depend. For example, halogen X2O7 is given, one of the species is there, right? So now what will be their characteristic properties? If we talk about oxides which are formed by these metals, right? For example, sodium plus oxygen, it will result in the formation of Na2, right? Half O2 we can take, okay? Na2 or 4Na, likewise it can be valid. So this Na2O is the oxide formed by alkali metals. Now what will be its character? So this sodium oxide, when it is dissolved in water, what will happen? It will result in the formation of NaOH. How many? 2 NaOH. So this oxide, metallic oxide, on dissolving in water or on reaction with water, has resulted in the formation of a hydroxide which is basic in nature, or we call them as alkalis. So this is basic in nature. So all the metallic oxides, they are basic in nature. This is the property you have already studied in your junior classes, basic nature, right? So in the same manner, whereas that formed by extreme right are the most acidic in nature. For example, Cl2O7, when it is dissolved in water, what will happen? It will result in the formation HClO4, perchloric acid is formed, right? Perchloric acid is formed. 2 moles of perchloric acid will be formed. So this is acidic, right? Then oxides of elements, now in the center. So we have analyzed the property. The elements which are present to the two extremes of the periodic table, they are most reactive, whereas the elements which are present in the center, they are less reactive. Now the oxides of elements in the center, so they will be amphoteric. Amphoteric nature means on reaction with acid, they will result in the formation of dissolving water, or with reaction acid they can also react. That is, oxides of elements of in the center are amphoteric. Amphoteric means they can react both with acid as well as with base, right? So aluminium oxide is there and arsenium oxide is there. Aluminium oxide is there, right? Or they might be neutral. So amphoteric are formed by the species which lie in the center, amphoteric oxides, which may be aluminium, arsenic, selenium, all these, or some of them are neutral, for example, carbon monoxide, nitric oxide, nitrous oxide, right? Amphoteric oxides, they behave acid and bases, right, depending on the nature. Whereas neutral oxides have no acidic or basic properties. So this was all about the compounds formed by various elements in the periodic table, general trends, right? Now towards the end, there is again one problem. Show by a chemical reaction with water that Na2O is basic, and this we have already discussed, right? Na2O will form sodium hydroxide, whereas Cl2O7 it will form perchloric acid. You can see this, it's given Na2O, H2O, 2NaOH, and whereas Cl2, H2O, HClO4. So this is acidic and this one is basic. So we have concluded this already, that metallic oxides are basic, non-metallic oxides are acidic in nature, right? The rest properties we will analyze about transition elements. Transition elements, we will study them differently. They have slightly variation or deviation from these, but S and P, they show almost similar properties. That is, one is, both are highly reactive, and that's why they are called as representative elements. With this, we have completed this chapter, right? Thank you.